Friends, basic principles of feedback control were under discussion. We had been discussing last time about the sensitivity and robustness issues. Let me reconsider the basic block diagram. This is the controller with transfer function D. Here I have the plant with the transfer function G. The disturbance to the plant has been modeled through a transfer function N, and here is a disturbance input W. The output is Y. This output Y is fed back through the sensor with transfer function H. Here is an error detector and my reference input is R over here. This we have taken as the error signal E cap, and this has been taken as the control signal U. This is the basic block diagram with respect to which the basic characteristics of feedback control systems are being discussed. The transfer function between Y and R is given as Ys over Rs. We have designated it by Ms is equal to, as you know, ds gs over 1 plus ds gs hs. This is your overall transfer function of the closed loop system. The basic result we derived last time was that the sensitivity of the overall transfer function M with respect to the plant transfer function G. Please note that I am assuming that there are certain parameters of the plant which are subject to variations, and therefore I am studying the sensitivity of the overall transfer function with respect to plant, which is equivalent to studying the sensitivity of the system response to variations in the parameters of the plant. It's just equivalent. Instead of the response here, I am taking the overall closed loop transfer function, and instead of the specific parameters theta, I am taking the plant transfer function to which the parameters theta belong. Okay? This, if you recall, was derived to be equal to 1 over 1 plus ds gs hs. To make it very clear, let me put it here that this is actually g theta ns, meaning thereby that theta, the parameter under variation, belongs to the plant G. One more transfer function, sensitivity function we derived, that was S of M with respect to H, that was equal to minus ds gs hs divided by 1 plus ds gs hs. This is the sensitivity of the overall function with respect to the H, that is the sensor transfer function. Now please see what were the conclusions. Last time we came to the following conclusions. Number 1, if I increase the loop gain, here is the loop transfer function. Please see, loop transfer function. Come back to this particular slide. You will find that this is the loop, and if I multiply all these blocks d, g and h, I get the loop transfer function dgh. And if I increase this loop gain, in that particular case I find that sensitivity of M with respect to G reduces. Okay. Now as a comparative index, it will be interesting if you keep the sensitivity of M with respect to G is equal to 1 also into focus, and this is the sensitivity of the open loop system. When you break the loop, then the sensitivity of the open loop system is unity. That is, the open loop system is highly sensitive to parameter changes in the plant. So if I increase the loop gain, you please note that sensitivity reduces with respect to this sensitivity. This is one of the important attributes of feedback control. Okay? Look at the sensor. Please see, if I increase the loop gain, the sensitivity of M with respect to H tends to 1, which indicates that the closed loop system is highly sensitive to parameter changes of the sensor. Therefore, at the design stage as a control engineer, we have to be extra careful in selecting the sensors the sensor should really be a robust and stable sensor, that is, the components or the parameters of the sensor should not change with environmental and other conditions. This should be our selection as far as sensor choice is concerned. Okay? One point here to be noted, what is the price we are paying in terms of improving the sensitivity? You will please note that if I consider the open loop system, here is the open loop system D and G. I need your attention here, please. This is your input R, this is your output Y. You find that the gain of the system is given by D into G. Ys over Rs is equal to ds into gs. So it means Ys is equal to this much of system gain multiplied by Rs. But what happens in the case of a closed loop system? Ys over Rs is equal to, as you see, ds gs over 1 plus ds gs hs. You will please note that we are immediately paying a price for sensitivity improvement, and the price is in terms of loss of gain. The output in this particular case is equal to this particular function multiplied by input, while the output in this case is this much of function multiplied by input. Higher the loop gain, better is the system sensitivity, that is, lesser is the effect of parameter changes on the system. But in addition, you will note that there is a larger price paid in terms of loss of gain. So you see that, well, though it is definitely a disadvantage, but the advantages outweigh this disadvantage, and this disadvantage can easily be taken care of by, you can just see, having an appropriate open loop gain in the system. You see that, suppose this is the motor, and if the open loop gain of the motor is made high, that is, the selection of the motor is such that the gain of the motor is high, if I will keep it high because I know that I am going to use it in the feedback loop, and in the feedback loop the overall gain of the system is going to be reduced. So it means the selection of the plant or tuning or the tweaking of the plant should be done in such a way that the open loop gain of the plant is high to account for the loss of gain which will occur because of the feedback action. So it means because of the feedback action there is going to be a loss of gain. Suppose in the open loop plant there was certain gain for G required. For the feedback action, the only precaution I can take is that the gain of G, somehow this much of adjustment I will make in the plant, that the gain of G is higher, because I know that when I connect a feedback loop the gain between Y and R will be reduced, and to keep it or to bring it to the acceptable limits I can take certain precautions, I can do certain adjustments on the plant model G, and this is the way I can accommodate for this loss. But however, you see that the sensitivity reduction is such an important parameter that the loss of gain is not considered to be a very significant disadvantage. Okay. Any question on this point, please?
So why do you need a high gain? You can always connect an amplifier at the end.
Okay, that is one point. Please see that he says that the controller transfer function, and here I take G, the plant transfer function. Well, the disturbance here is disturbance transfer function is N, disturbance is W. Let me take the output Y, reference is R, the sensor transfer function is H. Now Ys over Rs is equal to ds gs divided by 1 plus ds gs hs. Now because of this high loop gain, as we find there is a loss of gain, Y, the ratio between Y and R gets reduced, and he says that if I take an amplifier here, in that particular case this loss of gain can be compensated for. Good suggestion, but what will happen if the parameters of this particular unit outside the loop change. For example, let us say this is temperature and you want to increase the temperature, you want to magnify the temperature. The device for that particular purpose will have its own problems. The parameter variations of that particular device will affect the system output directly. Because this particular component is not in the feedback loop, the feedback strategy is not taking care of the parameter variations of this component. So it means any changes occurring within this component or any environmental effect on this particular component is going to directly affect the system output. And therefore, we try to compensate for the loss by putting sufficient margin or by increasing the open loop gain of the plant, so that after the loss of gain, the output level is acceptable to us. Okay. So now we have seen that compared to the open loop transfer function, which is ds, gs, y and r, compared to this open loop, the closed loop transfer function here, okay, let me forget about the disturbance for the time being, h, gives me better sensitivity properties, sensitivity reduction, which I may say that, please see, probably I think I have made a statement here, the robustness or sensitivity reduction is the primary goal of feedback action. Otherwise, probably all those other requirements of, let us say, the steady state accuracy or shaping the dynamic response or other requirements on the control system can suitably be met with an open loop control as well. You will see shortly, we are going to discuss today itself, that all those things which you have in mind, that the transient response should behave in a particular way, the required steady state accuracy should be this much, probably these can be met by open loop control also. Or if you don't mind, I can make a statement that they may be better satisfied with an open loop control compared to even feedback action. I may get better performance as far as dynamic shape is concerned or as far as steady state accuracy is concerned if there is no feedback action. However, you see, the real life problem is that of robustness or sensitivity. You cannot eliminate this problem, and hence you have to go for feedback action, and the feedback action is creating its own problems, and that is why the design becomes complex. It is really a suitable trade-off between the accuracy and the stability, and instability is caused because of the feedback action only, as you will see. So the feedback action is primarily coming for the robustness or sensitivity reduction, and it is going to create problems, and we have to suitably strike a compromise between the dynamic response, between the steady state accuracy, and between the robustness which you are going to achieve through feedback. Okay. Now next let me take the disturbance rejection. Sensitivity will be coming in detailed discussion later. Now it's only the qualitative appreciation I am going to give you, please. All these aspects of design naturally will come in depth when we take up the design aspects of control systems, but the qualitative appreciation must come today itself. This is the objective of today's lecture. Disturbance rejection, let me say, take this aspect. Now if you take the, let me not redraw it, let me project this slide. Now if you take W versus Y, the output, in that particular case you know that the transfer function is going to be Ys over Ws equal to, we have already called it MWs is equal to Ns divided by 1 plus ds gs hs. Please see, either you know it or you can derive it. I leave it to you that Ys over Ws, the transfer function between output and disturbance, is given by this function Ns divided by 1 plus ds gs hs. Okay. Now let me concentrate on this. Ys over Ws equal to Ns 1 plus ds gs hs. Now please see the effect of the loop gain or the feedback action on the disturbance rejection. Again, I think it's very clear that if this loop gain is made high, in that particular case the disturbance effect is filtered out or is reduced. So it means the rejection of disturbance is also directly related to the feedback property. If you make h is equal to 0, the disturbance rejection is not possible. All the disturbances which enter the plant will definitely show up their effect in the output, because you see that in the process of feedback your controller becomes intelligent because it has the information. You see that qualitative aspect of control action. Now because of the feedback action, DS is your controller, it has got the information about the effect of disturbance on the output. Since it has got information about the effect of the disturbance on the output, it can take appropriate action to reduce the effect of the disturbance. But as far as your open loop scheme is concerned, you just recall this scheme D and G. Let us say disturbance acts over here. The controller has no information about the disturbance at all. So if the controller has no information about the input disturbance, it naturally cannot take any effect to compensate for disturbance. It cannot filter out the effects of disturbances, and hence in an open loop scheme, if the disturbances come, they naturally will affect the output straight away. And disturbances, as we have seen through our practical case studies, through our hardware examples, we have seen the disturbance effects do come. In almost every case we have come across, we have seen that there was an effect of disturbance. So it means there is absolutely no alternative to feedback. You can never go for an open loop scheme, because in the open loop scheme the disturbances are going to directly affect the controlled variable. While in the case of feedback action, you find over here that by suitable control of the loop gain, I am talking of the loop gain again and again, and through this particular thing I can control the effect of Ws on output Y. Okay. Now at this point, one specific information I like to give, that as far as the loop gain is concerned, there are three parameters, please: HS, GS and DS. I assume that HS, the sensor, you cannot play with that sensor. You cannot increase the loop gain by increasing the gain of the sensor. Sensor itself has got certain constraints. The parameters of the sensors cannot be allowed to vary because the system is highly sensitive to sensor parameters. So sensor is fixed and is given by the considerations of robustness. The design is fixed for the sensor. How about GS? The plant gain also, in all probability, in most of the cases, cannot be varied. The plant is a fixed plant. The only parameter which is subject to change, which is subject to design, is the controller. You will actually change your DS so that the loop gain DS, GS, HS is increased, and hence the disturbance effects can be filtered out. Now one thing to be noted, suppose somehow you can change the gain of GS also. The loop gain through change in GS can be increased, no doubt. But one point may please be noted, you have to be extra cautious about it. What is NS after all? NS is the transfer function between the disturbance and the plant output. So naturally NS is a function of GS. You recall so many models we have derived for the disturbance models. In many systems we have derived, and we have seen that NS, the disturbance link between the plant output and the disturbance W, is a function of GS. So it may happen that if you change the loop gain through G, in that particular case it may increase the disturbance effect on the plant, because this G is affecting NS also, and this NS is appearing in the numerator. So it means, you see that, just don't go by this blind rule that increase of the loop gain will improve the disturbance or will reject the disturbance. How is the loop gain being increased? That is also important. If you increase the loop gain through G, there is a possibility that you are increasing the gain of N, and if you are increasing the gain of N, you are causing problems for the system rather than taking away the problems or finding the solutions to the problems. So this is all a complex situation, you see. It's not just goes sequential way that you increase the loop gain, it will reject the disturbances. You have to account for the total system in totality and see what are the parameters which are getting affected by change in gain of any of the components. Okay, but as a thumb rule I may tell you that we will not touch GS and HS. These may become our fixed components. Once you have taken care of, maybe by adjusting some open loop gain, you might have taken care of the loss of gain. After that, the loop gain is primarily being increased through the controller design DS. Okay, fine. Next I take noise filtering, and I need now, I think, your participation in setting up the characteristics of the system. Come on please, let us see what is the effect of feedback on the noise effect. We know that from where is the noise coming? The major source, the most important source of noise is the sensor itself. Okay, as we have seen in our system examples. So let me take a situation like this. D is my controller transfer function, G is the plant, this is output Y. So as soon as I try to measure it, I introduce a noise signal V, and let me say that this is being fed back. I am taking unity feedback case to simplify the situation. Okay, take this case only to make the discussion simple, otherwise it could be the more complete block diagram. There is absolutely no problem in that. Okay, now you have to help me please. This V is a high frequency noise, high frequency signal which is coming because of the sensor. Recall the temperature control system. Thermocouple being close to the tank which is being continuously stirred. Well, you see, you cannot avoid high frequency signals entering the loop, because after all temperature measurement is a must, and to measure temperature you have to install a measuring device. Suppose you install a thermocouple there, so you see that thermocouple is introducing the high frequency noise in the loop which otherwise was missing in an open loop scheme. So it means a sensor is the major source of high frequency noise in the loop. And let us see how is the loop gain going to affect this noise effect. And I want you to give me the transfer function between V and Y, V as the input and Y as the output. Help me please. I think you can just look at this block diagram quickly and give me the transfer function. I need the answer from you please. Ys over Vs is equal to what? Yes, I wait for a few seconds. Just minus dg upon 1 plus dg. That's right please. You can just view it as a basic feedback loop. This as a reference input, this as an output, this will become forward path transfer function minus dh. So it is minus dg over 1 plus dg. Now you see this effect please. Now in this particular case the loop gain is dg. You increase the loop gain. To increase the loop gain for sensitivity reduction or disturbance rejection is increasing your noise problems. You can just see that when you increase the loop gain, Ys by Vs is nearly equal to minus 1, and hence whatever is the noise signal over here, it is directly getting injected into the loop. So it means when you try to improve the performance in terms of disturbance rejection and sensitivity reduction, you are increasing the problems in terms of noise effect. Okay, well, as I said, there is always a trade-off in the control system design. You cannot meet all the requirements by increasing the loop gain. So what we normally do is the following, that to take care of the noise problem, we don't compromise on the loop gain, rather we introduce an appropriate high frequency noise filter. So it means we take care of the noise problem by introducing an additional component, an appropriate high frequency noise filter, so that this particular noise, the high frequency noise, is blocked by that particular filter and it is not allowed to enter into the loop gain. This will permit us to go for high loop gains for disturbance reduction and sensitivity reduction. This point may please be noted down, that the increase in the loop gain is creating problems as far as noise filtering characteristics are concerned. So it means again, at the sensor point you have to be extra careful. A suitable high frequencies, you will have to study the type of frequencies entering into the system. You will have to study the environment in which your sensor has been installed, the effect of the environment on the sensor, and what type of frequencies will enter through the sensor has to be studied, and then a suitable sensor filter, a suitable high frequency filter should be designed so that the high frequency signals are not allowed to enter into the loop, and hence this will not come on your way as far as taking high loop gains is concerned. Okay. Next feature I take, shaping the dynamic response. Shaping the dynamic response. You recall what do I mean by shaping the dynamic response? I gave you an example that if this is the value I want, I may be interested in this type of response. This is one typical example, and not in this type. This may be my requirement. It means I am giving the shape of the transient also, which the output is required to follow. Not only that, where the output should settle down. Okay. Now you see that if I give you a function ys over rs is equal to dsgs over 1 plus dsgshs, please recall, how do you shape the dynamic response? You will remember, I am sure, that the dynamic output y is a function of the system poles. As far as the zeros are concerned, they simply affect the magnitude of the various modes of the response, whether the response is oscillatory, whether the response is non-oscillatory, whether it is a first order factor, whether it is a second order response. All this is going to be guided by the poles of the system and not by the zeros. I hope you remember it very well. You can appreciate this particular point. As far as the zeros are concerned, they are, when you take the partial fraction expansion for example, the zeros will affect only the residues, magnitude, and those residues will affect the magnitude of the response. The nature of the response will guided by the pole. Okay. For example, if the pole is a first order factor, 1 over tau s plus 1 into a, in the numerator I have a1, the zeros only affect the magnitude of a1 and the poles affect the magnitude, affect this tau. And you know that if my tau is here, the response may look like this. An impulse response, let me take, impulse response may look like this. And if the tau is here, the impulse response may look like this. So in this particular case you find that the settling is quicker, while in this particular case the settling takes time. So it means, what I want to say is that the shape of the dynamic response is dictated by the poles of the transfer function, and the zeros of the transfer function only change the magnitude of the response. That is, your response may become like this depending upon the zeros effect. The response may become like this depending upon the zeros you may change. But as far as the shape is concerned, whether the response is this way, now your poles may be this way. If your poles are this way, you know that your response will be oscillatory in nature. Damped oscillations or undamped oscillations. So it means the nature of the poles is going to guide the nature of the response. Now let us see how will the feedback action affect this. This is what I want you to appreciate. Ys over Rs is equal to dsgs over 1 plus dsgshs. Let me take ds as a ratio of two polynomials, d1 by d2. A qualitative appreciation at this particular point is really needed. I take it as a ratio of two polynomials, G as a ratio of two polynomials, G1 and G2, H as a ratio of two polynomials, H1 and H2. And therefore, your MS becomes equal to, please see, D1, G1, I am directly writing H2 divided by D2, G2, H2 plus D1, G1, H1. Just see that. This is your MS. Okay, I hope this is okay. Just I have substituted these polynomial functions and I have rearranged. I get this as the rearrangement. Fine. Now please see, if you want to shape the dynamic response, it means you want to make it different from the open loop response, and the open loop dynamics is guided by G2, because G2 is going to give you the poles of G. So it means the pole locations of G2 are not acceptable to you. That is why you want to go and shape the dynamic response. So just see that the pole locations of G2 are not acceptable to you. By suitable design of D1 and D2, you can change the factors of this polynomial, and hence you can change the pole locations of the closed loop system, and therefore you can shape the dynamic response of the system. So through feedback action, I just want to say this point. You see that in the open loop case, the response G2 was not acceptable to you, but through feedback action you can appropriately choose D1 and D2, so that these roots of this particular equation, roots of this particular polynomial, which will become the poles of the transfer function MS, can be suitably placed in the S plane, and hence the dynamic shape of the response can be suitably given. Or whatever shape, what you will do is the following, that given the dynamic shape, you will translate that dynamic shape into desired locations of poles, and then you will select D1 and D2 so that those locations of poles are realized. See the design problem, please. I really will like confirmation from you that my point is followed. My point, I repeat, suppose I want this as the dynamic response. Of course the design methods are going to come, but my strategy will be the following. This dynamic response, let us say, can be realized by these pole locations. These two pole locations. Let us say I have given you the methods. You are equipped with the methods to establish this fact that the dynamic response of this shape can be realized if the pole locations are these. Now let us assume that your open loop transfer function does not have these pole locations. So in this particular case, I want to claim that by a suitable design of D1 and D2, that is by suitable design of the controller DS, you will be able to force the pole locations of the closed loop system onto these points, so that the dynamic response of the closed loop systems follows the prescribed dynamic shape. Is it okay, please? I hope you are getting my point. The prescribed dynamic shape can easily be realized by this way, by a suitable design of D1 and D2, so that the closed loop poles are same as these two pole locations. Please don't worry about the quantitative aspects, as I am telling you again and again. You try to appreciate the qualitative nature of the result. Okay, so this concludes that, well, shaping the dynamic response through the feedback action is possible if I appropriately design the controller and hence numerator and denominator polynomials of DS, so that the closed loop poles of MS are same as the closed loop poles which result in the required dynamic shape. Okay, but one thing is there, my friends, if really this is the objective, I can realize this objective. This statement I re-emphasized, and if this is the objective, probably this objective can be realized in a very simple way in the open loop control mode itself. Can you suggest how can I realize this objective? I make my objective clear once again. I want to change the poles of the system so that they become equal to the prescribed poles which correspond to the desired dynamic shape of the response. My question to you is this: can I realize this objective by open loop control? Recall the open loop control. D is here, G is here, there is no feedback action. This is R, this is Y. I want the poles of G are not acceptable to you. The poles of G are not giving you the desired dynamic response. I want to design a D so that the poles of this overall system correspond to the locations which is a result of the prescribed shape of the response. Come on, give me a suggestion, please.
D1 should cancel the pole of D2.
That's fine, fine.
And
And then give the other pole. It's wonderful, please. This is what I had in mind. You see, the most obvious solution which dictates as if feedback action is not required at all is this: first you cancel the poles of GS, that is, you make 1 over GS. So poles of GS are cancelled out, so they are not going to affect the dynamic mode at all. Into you prescribe the poles which you want, prescribed poles. Let us say your prescribed poles are S squared plus 2 zeta omega n S plus omega n square. Let us say this is the prescribed pole. Now if I take this GS, what is overall Y by R? You will please note that Ys by Rs is equal to 1 over S squared plus 2 zeta omega n S plus omega n squared, which you claimed is the situation corresponding to the given dynamic shape. So naturally, if such a ds is realizable, in that particular case, this is the most obvious and the exact solution which is possible. But we don't go for this solution. Any answer to this point? That we never go for this solution rather. Why? Though it is most obvious solution, we never go for this solution, please. Come on, I need again some idea from you. Okay, fine, doesn't matter. As soon as I give you the idea, you will definitely appreciate. You see that this ds, please your attention, this ds will cancel the poles of GS and not that of the actual physical plant, because the actual physical plant and GS which you are using over here, there is always a gap. We have said that you can never model a physical plant exactly. Since you can never model a physical plant exactly, it means when you use a controller ds realized from GS, it is not going to nullify the dynamics of the plant, though it is nullifying the dynamics of the model. So since there is always a gap between the model and the plant, this cancellation, as was suggested by one of you, is possible with respect to model only and not with respect to plant. And therefore there will be an error between Y and R because of this imperfect cancellation. And since the controller is not having any knowledge about the error, there is no feedback action going over here. So the controller is not intelligent controller, it has no information about the errors. Those errors will keep on building up and your system may become unstable. And therefore such a performance or such a controller in which an open loop pole dynamics cancelling attribute is used is never utilized. Not only the modeling errors, this G you have used once for all. D you are not tuning online because the parameters of G may keep on changing with time. The G parameters, the actual process, the G parameters will not change because G is only a model. But the actual system parameters will keep on changing with time, and this change in time is not reflected in D. This D is not an adaptive controller which adapts to the changes in the G parameter, and therefore with time the performance of this D will deteriorate. It is because of this sensitivity or robustness requirements that you never go for this open loop solution, though this open loop solution seems to be the most obvious solution possible. So though feedback action is more difficult, you will please recall that transfer function I gave you. Adjusting the closed loop poles of the feedback system is more difficult than realizing the poles this way. But we go for that difficult design procedure, but we do use our feedback principle to take account of robustness and disturbance rejection requirements. I hope this point is well taken. Fine. Now this way, let us go to steady state accuracy also. Similar thing. Steady state accuracy. Take the basic feedback loop G. Let me take it unity feedback to make it a little simple. Now you know that this is your error E. At this particular point, you have got the error E. Now please see in this particular case, Ys over Rs is equal to dg over 1 plus dg and Es over Rs. I leave it to you, a simple exercise. You can look at this block diagram or you can even give me please. What is Es over Rs? 1 over 1 plus dg, dsgs. Please check this point. This is your Es over Rs. Es is the error. This is 1 over 1 plus dsgs. This can easily be examined. Now what is the steady state error? The steady state error, we can use the final value theorem, limit s tends to 0, SES is going to become your steady state error. This is equal to limit s tends to 0, SRS over 1 plus dsgs. This is equal to, as you know, limit t tends to infinity Et. This I have the basic relationship for the steady state error using the final value theorem. Now take a specific case please. Again a very interesting result will come. Let me take Rs is equal to 1 over S. What is steady state error please? Let me call this as ESS. ESS equal to, come on please, 1 over 1 plus D0 G0. This is your steady state error. What is D0 G0? It is the DC gain of the loop. That is the loop gain at low frequencies. Substituting S is equal to 0 is equivalent to getting the DC gain of the loop. That is when the frequency signal is low. When the frequency of the signal is low, at that particular point, the gain of the loop is the DC gain. So it means 1 over 1 plus D0 G0 is the steady state error for the specific situation under consideration, and this is directly dictated by the DC gain. Yes, surely I can reduce the steady state error by an appropriate design of the controller. ESS is equal to 1 over 1 plus D0 G0. Make an appropriate design of the controller. Suitable control of the value D0 will give me the reduction in the steady state error and hence will improve the steady state accuracy. So keep this point in mind now, that steady state accuracy gets improved with increase in the loop gain. This is your loop gain after all, and I am improving the steady state accuracy with the increase in the loop gain. Come on please, now just let us compare this situation with an open loop situation. Help me here also, R and Y. What is the steady state error? E is equal to Rs minus Ys. Input minus output is the error. Is equal to Es, let me take it, is equal to Rs minus, help me please, ds gs Rs is equal to Rs into 1 minus ds gs. Okay, so it means, just please look at this point, steady state error becomes equal to, for a step input, you can see I will take Rs is equal to 1 by S and then apply the final value theorem. Give me the result for steady state error please. 1 minus D0 G0. See whether it is okay. I have substituted Rs is equal to 1 over S and then applied the final value theorem. Okay. Now from this expression, should I do it or it's okay? This expression from here please. Yes, I need, okay, fine. In this particular case now you see that you can reduce the steady state error to 0 by suitably designing D0. You make your D0 G0 is equal to 1. So again please see, probably the steady state accuracy requirements can be better met with open loop control than with feedback, if there were no problems as far as robustness and disturbance rejection requirements are concerned. You see that in this particular case probably you cannot reduce the steady state error to 0. You will have to make D0 G0 infinite. to make the steady state error 0. Well, in this particular case you can make the steady state error 0 by an appropriate design of D0. So it means I want to say is that what I want to say is that the open loop control has a solution as far as the dynamic response or steady state response is concerned. We are going for the feedback action primarily because of the sensitivity and disturbance rejection requirements, and those requirements are primary, and it is because of those requirements that we are first creating problems because of feedback and then solving those problems as a compromise between robustness and accuracy requirements or stability and accuracy requirements. We have to make a suitable compromise between the two solutions. Okay, this is what I had to say as far as the qualitative aspects of feedback control are concerned. I will really like to conclude this with certain summary points coming from you. We have seen all through that high loop gain is one of the design tools available with us. Maybe by high loop gain we are going to take care of many of the design requirements. Let us now list one by one what the high loop gain can do. Can it satisfy all the requirements, or it can create problems for us? High loop gain, as you have seen, sensitivity reduction is possible. That we have seen. 2. By high loop gain we have seen disturbance rejection is possible. And what else, please? You will tell me. By high loop gain you have clearly seen steady state accuracy can be improved. So it means if you go for a high loop gain, you find the higher the loop gain, just see a thumb rule, higher the loop gain, better is the performance of the system in terms of these three requirements. Let us see the problems. The high loop gain can raise certain problems. At least 3 of them I want you to list. Come on, please. The high loop gain problems. 1, we have seen the noise problems. That is, the high loop gain will allow the high frequency noise to enter the loop, and hence the signal to noise ratio may become poor and the performance of the system may become poor. What else, please? A high loop gain may create very high values of the input signals, please see, and your system under consideration or some of the components of the system may saturate. So the situation is not that simple that you will immediately improve the performance of the system by high loop gain. The system may saturate the sum of the components there, so those considerations will limit the high loop gain. The noise considerations will limit the high loop gain. You cannot take infinite gain because of the noise problems. You cannot take the infinite gain because of the input amplitude constraints. And the stability problems you will see, that is the transient response or the dynamics problems, that we will see later in details. That is, higher the loop gain, more prone is the system to instability. You will see there, higher the loop gain, more oscillatory the system becomes, and more oscillatory system can become unstable, and therefore high loop gain is limited from the stability requirements also. So it means the design is a trade-off between the various design requirements we have seen. The various design requirements have to be simultaneously met to see that the overall control objectives are satisfied. I will conclude my discussion with this statement that as far as this block diagram is concerned, the loop gain can be increased by appropriate design of D. The concluding statement, but very important statement, and the discussion on this statement will follow in the next lecture. D, increasing the gain is actually increasing the amplification gain. So your D may be an amplifier, for example. Please see, purely an amplifier. The gain of this particular loop can easily be increased by increasing the gain of the amplifier. It's so simple a situation. We have always been talking about the high loop gain. If you don't change the gain through G and H, it means you can change the gain through D, and most simple solution is changing the gain of D when D could be a simple amplifier. But we have seen that high loop gain is not the optimum solution, or may not give you the control solution in many situations. It means you will like to change this D, you will like to make it different from the amplifier. That is why the discussion of derivative and integral control has been coming. Please see, when only the gain, that is only the amplifier, cannot satisfy all the 6 requirements, you will like to change this D so that all the requirements are satisfied. And 2 of the things which we will be referring to, which we will be taking up, are the derivative action and the integral action. So you see now the need of derivative action and integral action. Your amplifier gain here, only amplifier gain, may not satisfy all the requirements. You have to look for alternative DS, and couple of suggestions are that in addition to the amplification, you take the derivative of E, and you take the integral of E and inject that particular signal in the loop. So it means in the loop, in addition to injecting a signal which is proportional to the error, you may inject the signal which is proportional to its derivative, and which is given by the integral of this particular signal. Now in the next lecture we have to see how this injection of proportional, derivative and integral actions is going to satisfy all the 6 requirements which we have imposed on our control system. Thank you.